So hello everyone, welcome to my talk today on compilation for emerging architectures, particularly near memory and in-memory computing architectures. So my name is Asif. I work at the Chair for Compiler Construction with Professor Geronimo Castrillon. At the Chair for Compiler Construction, we have different research lines from cyber physical systems to domain-specific languages to emerging architectures and compilers, of course. But today I'm going to mention only those which are relevant to ScaDS.AI. So, for instance, those which involve machine learning. So the first one that I'm going to talk about is machine learning for compilers. So we at the Chair, so some colleagues are working on using machine learning models to develop intelligent compilers. So for instance, in the case of CPU, GPU systems, if you have an input kernel, it's always a difficult task to decide where to map what. So for instance, it's always difficult to decide what to offload to the GPU and what should be run on the CPU. And we at the Chair, we have developed, so we are using machine learning models to develop intelligent flows that automatically decides when to map what to what architecture. And it's not only so we are not only using machine learning models to do the mapping, but we are also exploring machine learning models themselves. So for instance, in here in the graph on the right side, so we show that the graph-based machine learning models are superior to for instance, sequential models, in the sense that in terms of speed up, they are either comparable to existing models or are better, but when it comes to inference, they are orders of magnitude faster. And then we also use machine learning models in compilers to for instance, do optimizations. So in the case of CPU, GPU system, for instance, thread coarsening is one optimizations that you have to do. So sometimes it makes sense to merge multiple threads. So for instance, to reduce some overhead. So we're using machine learning in compilers to do that. And similarly, in polyhedral compilation, so code transformations is a routine task, but the space for transformation is usually quite huge, and it's always a complex task to decide the best set of transformations to generate efficient code. So we are using machine learning to identify the best code variants in terms of performance. So this is using machine learning for compilers. In another line of research, we are working on compilers for machine learning, and what I mean by that is that, for instance, you have a machine learning model implemented somewhere in a machine, in some machine learning framework like TensorFlow, Tensor Comprehension, PyTorch, or whatnot. And then the task is, how can you optimize this code, and how can you efficiently, for instance, map it to some hardware target. So in there, we are doing kernel level optimizations and target specific optimizations, hardware target specific optimization, which we will see in this presentation. For instance, by doing some classical loop transformations and so on. And we actually have a few running projects which is basically targeting this line of research. So for instance, we are part of the ScaDS.AI. We have a collaborative projects with AMD where we try to generate efficient code for their new AI engine. And then we are also working on compilation flows for emerging architectures under a special priority program of the DFG on the disruptive memory technologies. So today in this presentation, I'm only going to talk about, since this is a short presentation, I'm only going to talk about emerging architectures. And particularly, I'm going to focus on near memory and in-memory computing paradigms. But before talking about the compilation flow for these paradigms, I am first going to motivate. So why do we need these new architectures in the first place? And then the second question is, so what are the possibilities today? So what kind of architectures do we have? So let's start from the motivation. So if you look at today's system, so we have CPUs and memory, so they are kind of separated from each other, placed at different locations, and then they're connected through a narrow data channel, which is the memory channel. And the CPU is kind of playing the central role here. So whenever you want to do some computation, the CPU sends a data request to the memory to fetch data. The data is sent back through the channel to the CPU. It does the computation, whatever it wants to compute, and then it sends the data back to the memory. Now, if you look at the ratio of the execution time and energy consumption of the actual computation compared to this whole data shuttling going forward and backward, it looks quite scary, right? So for instance, if you look at an 8-bit multiplication, the energy required for the multiplication itself is 0.2 picojoule. But if you look at the energy required for accessing a word from memory, particularly DRAM, it's order of magnitude more expensive in terms of energy consumption. And if you look at the details, so in here we see for different bit weights and for different kind of operations, this trend remains more or less the same, that computation is order of magnitude cheaper than communication itself. So this is what we call the von Neumann bottleneck, and this kind of forced people to think of new computing paradigms, right? So for instance, instead of doing computation on the CPU part and storing data on the data part, so what we can do is we can actually move this computational part to the data part itself, right? And then we can do computation near the data. So we can basically compute data where it already resides. So there is no need to send it back and forth. So this is what we called near memory computing or in-memory computing. So the exact implementation of what we can do there and how we can do this. So this depends on the target system. We will see a few examples on the following slides. So for instance, if I talk about computation near memory, in there, you bring the compute logic, closer to the memory. So in here, I'm showing actually a real system that you can buy from the market today. This is from UpMem, which is a French-based company. And what they do is they take the DRAM, so they take the memory part, and then they fabricate, or they put the logic part on the memory chip themselves, right? So, and then you have like PIM-enabled chip, which is PIM is for processing in memory, and you have the conventional DRAM chips, right? So what they call main memory here. And whatever resides in this PIM-enabled chips can be computed with this computation unit, which they called data processing unit or DPU, on the same chip, right? So you can actually do computation closer to the memory. And UpMem is not the only example. So this is how the chip from UpMem look like. But UpMem is not the only example, right? So in recent years, we have seen other solutions. For instance, from Samsung, they are using, instead of the conventional DDR class of DRAM, they are using the high bandwidth memory, the HBM class of DRAM. But the idea in there is more or less the same, right? So they bring PIM units, processing in memory units, inside the DRAM chip. And that means you can use that PIM unit to compute on the data, or to operate on the data that resides in those banks. Similarly, there are CIM or compute in memory solutions where you basically exploit the properties of the device to do computations. So for instance, in here we are looking at a phase change memory device. So let's focus on this one G00 device. So whatever you store there, it's stored in the form of the resistance of the device. And if you apply some input some input voltage V, so depending on whatever is stored in the device, the current that you sense here is basically equivalent to the dot product of the product of the two values. And you can basically use it, extend it to do vector multiplication in one step, right? So if you can activate all rows, you store one vector in one column, as shown here in this red rectangle. You apply another vector as input, and in a single step, the current that you sense here at the sense amplifier is equivalent to the dot product of the two vectors. So this is particularly interesting for the machine learning domain, because in machine learning you have matrix multiplication, which is like a super important primitive, but it's computationally expensive. And with this in PCM computing, you can use you can do matrix multiplication in constant time. In here, it's in the analog domain, but I mean it's acceptable. And actually, there are now quite a few companies they're doing this, basically accelerating machine learning applications with these PCM or ReRAM based crossbars. But PCM is not the only technology, right? So if you look at the racetrack memory, so within racetrack, so you can implement a whole set of logic operations, you can implement arithmetic operations, you can do majority, and the same is true for other memory technologies. So for instance, with conventional DRAM, it has been shown that you can implement the whole set of logic operations. Same is true for SRAM, the same is true for FFET. And the bottom line is, in all available memory technologies today, you can do some sort of computations inside the device using the properties of the device. Now the question is, how do you program these devices? And this is something that we are going to see in this presentation in the following slides. So programmability is of these devices, to simply put, it's not straightforward, right? So if you look at the UpMem example, if you're a programmer, you are responsible to do load balancing in thousands of DPUs, right? So if you want to do matrix multiplication, you have to tell the device where you want to compute what elements. So load balancing is difficult, but it's not the only problem. Then you have to control the data movement. So within each DPU, so you have some memory. They have actually their own memory hierarchy. It's not a hierarchy per se, but so they use what they call main RAM or MRAM for short, which is still a DRAM, and then they have like this working RAM, which is a small scratch pad, and you have to control the data movement between MRAM and WRAM and so on. Similarly, as a programmer, it's your responsibility to take care of the data coherency. This can very easily get tricky if you are computing some parts on some DPUs, some other on other DPUs, and then eventually you have to take care of the partial results. If you look at the code, so in here on the right side, it's not complete code, but it's the code for a single thread on this UpMem system for matrix multiplication, right? So in here you are computing one element on a single thread, and in here the idea of showing it here is that you need to know all device details in order to write code for it. And actually the same is true for all these architectures, right? So if you're using the Samsung system, it's the same story. You need to know what kind of programming interface it offers. Then you need to understand that. You need to understand the device, and only then you can write efficient code for it. If you talk about SIM systems, it's the same story. They have their own programming models. You have to use them. You have to learn them, and then again, you need to understand the device properties in order to write efficient code for them. And as I showed on the previous slides, it's not a single system today. So we have like tens of systems, which means you have to be able to, if you want to write code for them, it means you have to understand all those systems and then their programming models, and only then you can do, which I think is extremely difficult, and maybe it's impossible, right? To support or to target all those devices. And the solution, therefore, we think is basically developing device-aware automatic compilation flows that take care of the hardware details and the lowering to these different hardware targets, right? So as a programmer, it should not be your responsibility. The compiler should take care of it. We started working in this direction like already a few years ago. So in 2021, for instance, we developed a compiler for these PCM-based accelerators, which we call OCC, the OpenSIM compiler. And in here, as I show here, it's based on MLIR. It's a hierarchical compilation flow. We start from tensor comprehension, and then so we have these different abstractions, these gray boxes here, for instance, Linalg SIM, and at each abstraction, so an abstraction, so for instance, in here, Linalg is a domain-specific abstraction, but SIM is a hardware-specific abstraction, so they can be domain-specific or hardware-specific, and then so we go from higher abstraction to lower abstraction, and along the way we do optimizations, right? And then you can, for instance, in here we introduce this SIM abstraction where we add optimizations and support for this PCM-based accelerators. So OCC support PCM-based SIM accelerators. As I said, it's the only technology it supports. But I mean, phase change memory-based, but resistive RAM is mostly similar. So that's why I think it's safe to say it supports memristive technologies. And as I said on the previous slide, this kind of accelerators or devices are particularly good for matrix model like operations, and that's why we only detect, so OCC automatically detects matrix like operations in the input code and then upload it to the device. These devices, so all memory arrays are of fixed size, but the input can be huge, and that's why you have to basically split the input sometimes, depending on what is the input size. if it is needed, the compiler in this case automatically takes care of tiling the input code and then uploading it to the accelerator. But it's not only doing the offloading. As I said before, OCC is also taking care of device-specific optimization. So for instance, it rewrites, when possible, it performs loop unrolling, which is again a compiler transformation to maximize parallelism. And in general, the write operation in these emerging memory technologies like phase change memory and resistive memories, it's slow and it requires a lot of energy. So that's why OCC tries to minimize the number of writes to the device by, for instance, changing loop order. And it also takes care of operators rewriting when possible, right? So for instance, if you have a convolution, we know we cannot directly execute convolution on the CIM accelerator, but we can rewrite it with some pre-processing. We can rewrite it as matrix multiplication. So OCC does that, and then it offloads it to the CIM accelerator. So OCC was already good, and we showed that with this we can automatically handle like a whole set of benchmark, but it supports only a single technology. And I showed in the previous slides that right now we have like a whole landscape of these technologies. So we started generalizing OCC recently. So we started from a partial taxonomy of the architectures that exist out there today. So for instance, we have CIM system, CNM system. In the CNM systems, UpMem, we show here UpMem, highlight UpMem because UpMem is the system that you can actually buy. So it exists, the actual hardware exists. On the same side, these memristive technologies are relatively more mature. We have a simulation infrastructure for that. So that's why for now, we develop a compiler where we have for now support for these two backends, but eventually, so all the systems in here and actually more will be added to the compilation flow. So we develop a compilation flow called Cinnamon. It's similar to OCC, is a hierarchical flow which implements both domain and device specific abstractions. So you can enter the compilation flow from some high-level description written in, for instance, TensorFlow or Tensor Comprehension. Then we have domain-specific abstractions like linalg, and then we have device-specific abstractions, right? So for instance, in here we have in the Cinnamon UpMem, and all domain and device-specific abstractions take place on their respective dialects or abstraction levels. So we go from higher abstraction to lower abstractions, and along the way, we actually perform optimizations. So for instance, in the case of UpMem, we perform UpMem-specific optimizations. And in the case of memristor, we implement memristor-specific optimization, which are very unique to the device. So if you look at so this is the code that I showed previously also. It's not in kind of a representative code for matrix multiplication on UpMem. So if you as a programmer are writing this code, you have to write it like this. But if you're using compilation flows like Cinnamon, as I said before, you do not need to know anything about the hardware. You can write device-agnostic code, and the compiler automatically takes care of generating this device-aware optimized code. If you look at the lowering, so you do not need to understand everything here, but I just wanted to show that the compiler eventually generates something which looks very similar to what you're writing today. For UpMem, we showed in terms of performance, so we showed that on selected benchmarks, the code generated by Cinnamon is comparable to the hand-optimized code. So in here, again, so we show that with Cinnamon, we can handle a whole set of benchmarks from so kernels and also complete applications like MLP. We have in here convolutions, contraction, matrix multiplication. We also show that we have different system setups, right? So DPU 1D and 5D and 10D are, so D is for DIMMs. So we have different system setups, and we start from a naive code, and then the compiler automatically generate optimized code. So all these OPT configurations are the compiler generated code. And if you look at it, so in here we have a very light green bar. I'm not sure if you can see it, but so the one on the for each benchmark, the bar on the extreme left is kind of the 1D naive, and then you have the 1D optimized, and then 5D naive, and so on. And in here we show that the compiler, the generated code is considerably better compared to what you write as a programmer, like like the naive code compared to the naive code. So for now, as I said, we are supporting we have active support for 2 hardware targets, and then we are planning to extend it by adding more hardware targets. So with this, I'm going to summarize my talk. I showed that in the very beginning, I showed that in data-intensive applications, application domains like machine learning, the data movement dominates both the execution time and the energy consumption. The solution is basically to move to emerging architectures like near memory and in-memory computing, because with this you can achieve orders of magnitude reduction in the execution time, and you can reduce also the energy consumption by orders of magnitude. But for these novel architectures to go mainstream, we have to make them accessible. We have to ease the way we program them. We have to make it easy and accessible to everyone. With Cinnamon and with OCC, we have started taking steps in that direction, but it's still an early work. We need a lot more research to better understand these systems, their requirements, their optimizations, and only then, once we understand them, we can actually implement them and integrate them in these automatic compilation flows. So with this, I would like to thank you all for your attention, and I'm now ready to take your questions.